Hello, welcome to CHE2511 Basic Organic Chemistry, and today we'll be looking at stereochemistry, specifically EZ isomerism. So what is EZ isomerism? E and Z isomers are simply geometric isomers or geometric stereoisomers of alkenes that are determined by the positions of high priority groups on a double bond. Why use them and what do they actually mean? E and Z isomers are not different from cis and trans isomers, except E and Z isomers are used when cis and trans terminology is ambiguous, specifically when we have four different groups on the double bond. So what do they actually mean? E means the highest priority groups are on the opposite side, and Z means the highest priority groups are on the same side. The memory aid that I usually use to memorize this is E for opposite, like opposite, and Z for the same side. So this is the memory aid that I use. And how do you assign priority? Priority is assigned by simply following the CIP rules, the can ingot prelog rules, the same rules that we use for assigning RS. So we try to look over these compounds that have been given and try to draw them based on what has been given. So for example, draw the structure of the following compounds, and A is 2Z3-isopropyl 2-heptene. So whenever you're drawing a structure, you first start with the parent. You have to identify your parent chain and the substituents. So in our structure, and by the way, E and Z are for double bonds. We use them for double bonds. So in our case, the first compound that has been given is 3-isopropyl 2-heptene. So the parent is a heptene. 2-heptene meaning the double bond is on carbon number 2. So 1, 2, 3, 4, 5, 6, 7. Heptene has 7. You write your parent chain first. And then on the parent chain, this is carbon number 1, this is carbon number 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So there is one carbon extra here that we have to remove. Then on carbon number 2, we have a double bond on carbon number 2. So 1, 2 between carbon and 2. Since it's 2-heptene between carbon 2 and 3, that's where we have our double bond. We have our double bond there. And when we write out our parent chain, we now go to the substituents, and the only substituents is 3-isopropyl. And 3-isopropyl, it means on 3, that's why we have our propyl group. This is isopropyl with 3 carbons. And once we do this, we try to verify the name. The name is 2Z. 2Z means they are on the same side, the highest priority groups. So the highest priority groups, when you look at the double bond is between carbon number 2 and 3. So you go at each carbon 2, you assign the priority groups, or you assign the priority to the groups that are attached on carbon number 2. And again, you come on carbon number 3 and try to assign the priority on the groups that are on carbon number 3. So how do we do that? We come on carbon number 2 and we look at the groups that are directly attached to carbon number 2. So if we look at carbon number 2, the groups that are on carbon number 2 are hydrogen here, there's an invisible hydrogen, and the methyl group this side. So if we assign priority is assigned based on atomic number. Hydrogen and carbon since it's the carbon of the methyl group is the one that is directly attached to this carbon on carbon 2. So a carbon and a hydrogen, the highest priority group is a carbon. So carbon would give it an A. And hydrogen a B. So you have assigned priority between these two groups on carbon number 2. And if we come on carbon number 3, we do the same thing. The groups that are attached here are this carbon and this carbon. So we try to assign priority, and if there is a tie breaking, if atoms are identical, we check the next atoms in the substituent chain until a difference is found. So here, for this carbon number 3, it's directly attached to this carbon 4 and the carbon here. So I usually use the dot method when I'm trying to break the tie. The dot method is the carbon that is directly attached to this carbon, or carbon of significance. So it's this carbon, we put a dot here, and this carbon, we put a dot here. And then we look at the groups that are directly attached to this carbon, starting with the one that has the highest atomic number. The 3 groups that are attached to this carbon. The 3 groups that are attached to this carbon are hydrogen here, hydrogen, and the carbon. So I write them starting with the one that has the highest atomic number. And I do the same for here. The 3 atoms that are attached to this carbon are carbon, carbon, and the hydrogen. So I write them according to the highest atomic number. So it's carbon, carbon, and not carbon, hydrogen, hydrogen. Okay, so it's carbon, hydrogen, carbon, carbon, and hydrogen. And then I compare these atoms, carbon, 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 hydrogen. So this carbon has highest priority compared to the hydrogen. So automatically this will be the highest priority group, and I'll give it an A. And then this carbon, I'll give it a B. And when you do that, it means you've assigned priority for all the groups that are attached to these carbons of a double bond. And then you come back and say A is highest priority, A is highest priority, B is the least priority. So if A and A are on the same side, it means the highest priority groups are on the same side of the double bond. Like our case, B is this side, B is this side, AA, it means the highest priority groups are on the same side. So this compound is 2Z3 isopropyl 2-heptene. Let me write it properly. So I like writing my double bond here. So when we do this is 2Z3 isopropyl heptene. So we try to do we try to do the same things for the next compound. We have 3Z, 6E, 6 bromo 3 ethyl 7 methyl 136 decatriene. So we do the same thing for this compound. We are on B now. So B, we also do the same thing. If you're trying to write the structure of the compound from a name, you always start with the parent chain. And the parent chain is 136 decatriene. Deca is 10 carbons, if I'm not mistaken. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I like numbering my carbons for easy explanation. 5, 6, 7, 8, 9, and 10. So you do the same thing for this. I'll first start by drawing out the parent chain, which is 1 between carbon 1 and 2. We have a double bond. Between carbon 3 and 6, between carbon 3 and 4, we have a double bond. And between carbon 6 and 7, we also have a double bond. Let me just put it here. I'll write it out properly. And then when you do that, you also write out the substituents. The substituents, we have got on carbon number 6, we've got a bromine. And on carbon number 3, we've got an ethyl. Carbon number 7, a methyl group. On carbon number 7 we get a methyl group. So this is just like a structure. Let me just write it properly. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This here we've got a methyl group. Carbon 1 here. We've got a bromine here and a methyl here. So this is our structure. So now it means on carbon number 3, the double bond that is on carbon number 3, the double bond on carbon number 3, it should have a Z conformation. I mean the stereochemistry should have Z, and on double bond that is on carbon number 6, it should be E. So Z means the highest priority group should be on the same side on carbon number 3. So if you come on carbon number 3, which is here, we've got this carbon and this carbon. The groups that are attached to this carbon and this carbon here, we'll look at this carbon here. We've got a hydrogen and a carbon. So automatically this is our A and this is our B, our hydrogen, our invisible hydrogen. And when we come here, we do the same. The groups that are directly attached to this carbon, we have a carbon here and we have a carbon here, and we have a tie. So for us to tie it or to break the tie, we use a dot method. Then we write out the bonds, the atoms that are directly attached to this carbon here. The 3 atoms, hydrogen, hydrogen, and carbon. Starting with the one that has the highest atomic number. And we do the same for here. So this is the atoms that are directly attached to these atoms are carbon. So since we have a double bond, we consider it as 2 single bonds to the same atom. So carbon, again carbon. So we have carbon, carbon, and then we have a hydrogen here. So automatically this is A. This carbon here is A and this is B. If you compare, this is CCH, this is CHH. C is highest compared to hydrogen. So automatically this is A. So on this side of the double bond, on this carbon, A is the highest priority is this side, and here the highest priority is this side. So here it means these guys are on the opposite side. We need them to be on the same side. So I will draw out my structure in such a way that I'll take this group here and bring it here, and this ethyl group I'll take it this side of the double bond, and this group I'll take it here. So in short, I will just put a double bond here and then remove the double bond there. It's just the same. Just the same structure. Just the same, I should have just written it. Remember, it's the same structure. I've just gotten this ethyl group that was here, taking it this side. And then the double bond, I'll bring it this side. Remember, it's just the same compound. So now we have, this was our A and this was our A. So now these groups are on the same side of the double bond. So we are done here. This is Z. And then we have to go on 6. The double bond on carbon number 6 is between this guy and this guy. So we need the highest priority groups here to be on the same, to be on the opposite side, since it's 6E. So we come on this carbon and this carbon. And this carbon is directly attached to bromine, and this carbon here. These are the two groups on this carbon, a bromine atom and a carbon. Automatically bromine has the highest atomic number, so it will be A and this will be B. And you do the same for this carbon. It's directly attached to this carbon, and this carbon. So to break a tie, you use the same dot method, and then you see the atoms, the three atoms that are attached to this carbon, a carbon and two hydrogens. Whilst for this carbon here, it's just three hydrogens because it's a methyl group. So automatically this is the highest priority A. But then we need them to be on the opposite side. So bromine and this 1, 2, 3 propyl group should be on the opposite side of the double bond. So in short, I'll need this methyl, this should be a methyl, this methyl should be this side, and then this whole group, the 1, 2, 3 chain should be this side. So I'll just do the same. Instead of rubbing it, I'll just do it like this. So I need the ethyl group, the methyl group, sorry, this side, the double bond, and then the three carbons this side of the double bond. So this structure is just okay, but then you can write it properly. But it means that this group, this other group of the, when this double bond is on the opposite side with this, because this was a priority A, so it was the highest priority. And then this group was B. Sorry, the A is this group, this B. So A and A are on the opposite side of the double bond. So meaning bromine is with a metal, and then this whole propyl group, 1, 2, 3 propyl group is on the opposite side of the double bond. So this is the highest priority here, and this is the highest priority here on the opposite side, which is E. And when you do this, then you would have drawn your structure. So the same can be done for compound C and D. So E and Z geometric stereoisomerism is just the same as cis trans, except a case where you've got 4 different groups that are attached to this on this double bond, 2 groups. So we try to get rid of that ambiguity. So we use EZ isomerism instead. So yeah, that was all for this class on EZ isomerism.